Hello friends, the topic of today's discussion is Diels-Alder reaction and overview. These are the points which we will discuss in this lecture. General introduction, reactivity of the two components dienes and dienophiles, regioselectivity and stereoselectivity of the Diels-Alder reaction. Diels-Alder reaction is a pericyclic reaction. It's a 4+2 cycloaddition reaction between a conjugated diene and a dienophile under thermal condition to produce 6-membered cyclic adduct. Instead of diene, we can have alpha-beta-unsaturated aldehyde, alpha-beta-unsaturated ketone, or alpha-beta-unsaturated imine. Instead of alkene, the dienophile can be alkyne, nitrile, nitroso, aldehyde, ketone, imine, azo compound, etc. If the Diels-Alder reaction leads to the formation of heterocyclic adduct, then it is called Hetero-Diels-Alder reaction. Reaction of butadiene with alkyne gives cyclohexadiene derivative. Reaction of butadiene, for example, 1-methoxy-3-trimethylsilyloxy 1,3-butadiene reacts with an aldehyde to produce 3,6-dihydro-2H-pyrene derivative, which after treatment with trifluoroacetic acid gives gamma-pyrone derivative. Similarly, reaction of substituted butadiene with cyclohexanone produces spirocyclic 3,6-dihydro-2H-pyrene derivative, which after treatment with acetyl chloride gives spirocyclic gamma-pyrone derivative. Reaction of substituted butadiene with imine like ethylmethylene carbamate gives 1,2,3,6 tetrahydropyridine derivative. Ethylmethylene carbamate is in situ generated from diethylmethylene dicarbamate under heating condition. Reaction of substituted butadiene with nitroso group like T-butyl nitroso format gives 3,6-dihydro-2H-pyrene 1,2-oxazine. T-butyl nitroso format is in situ generated by the reaction of N-Bock hydroxylamine with NaIO4. Reaction of diene with electron deficient nitrile gives 2,5-dihydropyridine derivative. For example, reaction of silyl-enol ether of cyclohexanone with paratoluene sulfonyl cyanide gives this bicyclic adduct, which after hydrolysis gives isoquinaclidinone 2-aza 2,2,2-octa 3,5-dione. Reaction of butadiene derivative with azo compound gives tetrahydropyridazine derivative. For example, this butadiene derivative undergoes Diels-Alder reaction with lead to produce this tetrahydropyridazine derivative. Reaction of alpha beta unsaturated aldehyde with alkene gives 3,4 dihydropyrene derivative. Similarly, reaction of alpha beta unsaturated ketone with alkene gives 3,4 dihydropyrene derivative. Reactivity of diene and dienophiles in Diels-Alder reaction. In Diels-Alder reaction, under normal electronic demand, HOMO of diene combines with the LUMO of dienophile to form Diels-Alder adduct. There are two components in Diels-Alder reaction, diene and dienophile. So the rate is affected by the nature of diene and dienophile. Let's first discuss the reactivity of diene. The reactivity of diene is increased by the following factors: ability of diene to adopt S-cis conformation, planarity of the system, and electron donor groups. Let's take the example of 1,3-butadiene. This is S-trans form and this is S-cis form. S-trans means the two double bonds are trans in reference to the single bond, and S-cis means the two double bonds are cis in reference to the single bond. S-trans is more stable than S-cis because of less steric hindrance. S-cis undergoes Diels-Alder reaction while S-trans does not. So, any factor that favors S-cis conformation increases the reactivity of diene towards Diels-Alder reaction, while any factor that favors S-trans decreases the reactivity of diene towards Diels-Alder reaction. So, the dienes with the enforced S-cis conformation have exceptionally high reactivity. For example, reactivity of 1, 2, and 3 is higher towards Diels-Alder reaction with maleic anhydride than 4, 5, and 6 because in 1, 2, and 3 the diene is locked in S-cis conformation. Compound 7 is more reactive than compound 8 because in compound 8 S-cis conformation is less favored due to steric hindrance. Compound 9 and 5 have higher reactivity than compound 6 due to the presence of electron donor group, and also presence of these groups disfavor S-trans conformation and favor S-cis conformation. Compound 9 is more reactive than compound 5 because in compound 9, due to bulky T-butyl group, S-trans is not favored and S-cis is more favored. Compounds 7, 10, and 11 are more reactive than compound 6 due to the presence of electron donor groups. Among these four compounds, 11 has highest reactivity, after that 10, and then 7. This is because NN dimethyl group has higher electron donating tendency than methoxy, which in turn has higher electron donating tendency than methyl group. Generally, substituents at position 1 have larger reactivity effect than substituents at position 2. For example, compound 10 with methoxy at position 1 has higher reactivity than compound 12 with the same methoxy group at position 2. Due to the same reason, 7 has higher reactivity than 5. These are the examples of dienes that are completely unreactive towards Diels-Alder reaction. Compound 13 and 14 are unreactive because the diene is locked in S-trans conformers. Compound 15, 16 and 17 are unreactive because S-cis conformation is highly destabilized due to strong steric repulsion, and compound 18 is unreactive because of electron withdrawing nature of chlorine and also destabilization of S-cis conformation due to steric hindrance. Now we will discuss reactivity of dienophiles in Diels-Alder reaction. These are the following factors that enhance the reactivity of dienophiles towards Diels-Alder reaction: electron withdrawing groups, a weak pi bond, and release of ring strain. This is a series of compounds showing relative reactivity of different compounds with respect to acrylonitrile, where we can see that more the electron deficiency in dienophile, higher is the reactivity. This is one more series in which monosubstituted dienophiles are arranged according to their relative reactivity with respect to acrylonitrile, where we can see that the reactivity increases with the increasing electron withdrawing tendency of the substituents. Propiolonitrile is far less reactive than acrylonitrile because the double bond taking part in Diels-Alder reaction is not in conjugation with electron withdrawing nitrile group, as it is perpendicular to the nitrile triple bond. This is another series. This is a series of reactive unactivated dienophiles. These are reactive because there is release of ring strain after Diels-Alder reaction. Regioselectivity of the Diels-Alder reaction. The regioselectivity of the Diels-Alder reaction of unsymmetrical diene with unsymmetrical dienophile can be predicted by orthopara rule. In general, one substituted dienes and monosubstituted dienophiles react to give orthoadduct as the major product. Two substituted dienes and monosubstituted dienophiles react to give paraadduct as the major product. Let's understand these points with the general structure. If we have a monosubstituted diene and a monosubstituted dienophile, there are two possible regioisomeric products. Orientation of diene and dienophile like this will give orthoadduct, while orientation of diene and dienophiles like this will give meta-adduct. According to the orthopara rule, orthoadduct will be the major, while meta-adduct will be minor. Similarly, two substituted diene and monosubstituted dienophile can orient like this to form para-adduct, or they can orient like this to give meta-adduct. According to the orthopara rule, para-adduct will be the major, while meta-adduct will be minor. This rule is true for almost every combination of electron withdrawing and electron donating groups, except one case where X and Y both are electron donors. In this case, there is marginal meta-selectivity. For more clarification, let's have some examples. For the clarification of first point, the substituents X and Y along with the percentage product distribution have been shown in this table. Here we can see that irrespective of the nature of X and Y, whether they are electron donating or electron withdrawing, orthoadduct have been found to be the major adduct. In the case of 3, 4 and 5, there was only orthoproduct. Meta-adduct could not be even detected. For the clarification of second point, let's have another table. In this case too, we can see that irrespective of the nature of the substituents, para-adduct is the major adduct. In some case, like example 13 and 14, formation of meta-adduct could not be even detected. Directive effect of substituents at position 1 of diene is higher than the substituent at position 2. For example, methyl penta 1,3-diene reacts with methyl acrylate to produce a mixture of regioisomeric product A and B. Product A, formed by the directive effect of methyl group at position 1, is 91%, while compound B, formed by the directive effect of methyl at position 2, is only 9%. Reaction of compound C with methyl acrylate gives only product D, which is formed by the directive effect of substituent at position 1. Stereochemistry of the Diels-Alder reaction. In this, we will first discuss the stereochemistry of the dienophile part, and then exo and endoproduct formation and endoselectivity. Relative orientation of groups in the dienophile remains unchanged during the course of the Diels-Alder reaction. This means two groups which are cis in the dienophile will remain cis, while those which are trans will remain trans in the Diels-Alder product. For example, reaction of 1,3-butadiene with cis-methyl crotonate gives cis products, and reaction of 1,3-butadiene with trans crotonate gives trans product. Similarly, reaction of 1,3-butadiene with maleic anhydride, which is a cis dienophile, produces cis product. Exo and endo product and endoselectivity. Exo and endo product formation comes into existence when at least one terminus of the diene has two different groups. Let's have this hypothetical diene. I have labeled the outer group as O and the inner group as I. I have taken alpha beta unsaturated aldehyde as a dienophile. The four groups of the dienophiles are CHO, A, B and C. During the reaction, the double bond will be developing here. There are two ways in which the dienophile can orient in the transition state to form diastereomers. The diene can orient like this, where the pi bond containing group, which is CHO in this case, is directing away from the developing double bond. If we view from this side, the product will look like this. This product, in which the outer group and the pi bond containing group are trans, is called exoproduct. The another way of orientation of dienophile is like this, where we can see that the electron withdrawing group is directing towards the developing double bond. If we view from this side, the product will look like this. This is another diastereomer in which we can see that the outer group and pi bond containing group, which is CHO, are cis to each other. This is called endoproduct. Exoproduct is thermodynamically more stable than endoproduct. Endoproduct is formed at faster rate than exo. So, exo is thermodynamic while endo is kinetic product. This is because the transition state for endo is more stable than exo. So, we get endo product as the major product. It would be easier to understand this if we go through Haeckel molecular orbital diagram of the transition state of endo and exoproduct. Haeckel molecular orbital diagram of exo transition state. In a Diels-Alder reaction under normal electronic demand, HOMO of diene combines with the LUMO of dienophile. This is the HOMO of diene and this is the LUMO of dienophile. For more details about the way of making Haeckel molecular orbital diagrams of different alkene and polyenes and structure of HOMO and LUMO, please visit my previous lectures. Their links have been shared in the comment section of this lecture. After reaction, the double bond will develop here. This is CHO group away from the developing double bond. These are the primary orbital overlaps responsible for the bond formation. Haeckel molecular orbital diagram of endo transition state. Just like exotransition state, this is the structure of HOMO of Diene and this is the structure of LUMO of dienophile. After reaction, the double bond will develop here. This is CHO group directing towards the developing double bond. These are the primary orbital overlaps responsible for the bond formation. This is an additional orbital interaction called secondary orbital overlap that provides additional stabilization to the endo-transition state. So, endo-transition state is more stable than exotransition state because of secondary orbital overlap. Let's take the example of reaction of 1-methoxy-1,3-butadiene with methyl acrylate. For our understanding, let's do arbitrary labeling of atoms participating in Diels-Alder reaction as 1, 2, 3, 4, 5 and 6. We already know that it would give ortho-regioisomer. After Diels-Alder reaction, the skeleton of the product will look like this. Now, put the atoms and groups at their respective positions. At C4 and C5, there are only hydrogen atoms, so put hydrogens at C4 and C5. We know that in endoproduct, the outer group in the diene and electron withdrawing group in the dienophile are cis to each other. So, methoxy at C1 and ester at C6 would be cis like this. Now, the remaining two hydrogens will automatically be cis to each other. You can simply draw this structure like this. This is the structure of one of the two endo enantiomers. The structure of second enantiomer will be like this. These endo products will be the major product. In exoproduct, methoxy and ester group will be trans to each other. So, the structure of the exoenantiomer can be like this. These will be minor products. Let's have another example in which cyclopentadiene reacts with ethyl acrylate to produce Diels-Alder adduct. For better understanding, put the missing hydrogens at the termini of the diene. In this case, the outer groups in the diene are hydrogen atoms. So, Diels-Alder reaction will give an endoproduct in which hydrogen and ester group will be cis. There will be one more endo-enantiomer which can be drawn like this. The structure of exoproduct can be drawn like this, in which hydrogen and ester group will be trans to each other. The another enantiomer of the exoproduct can be drawn like this. These are the top views of the Diels-Alder adducts. If we view this endoproduct from the lateral side, it would look like this. Similarly, if we view the exoproduct from the lateral side, it would look like this.